Welcome to European Microwave Week. We are here at the Rohde Schwarz booth where we show a joint demonstration between Cadence and Rohde Schwarz. My name is Markus Lerner, I'm with Rohde Schwarz, and with me is
Andy Wallace. Good morning, it's a pleasure to join you. Thank you, Markus, for inviting us to share with you for the integration of the tools together.
Thank you, Andy. What we want to talk about today, or what we want to show you briefly here, is a joint demonstration. Now, when you're designing an RF front end, you typically start with a simulation. And for running simulations, we are partnering here with Cadence, and that is also what we are showing here on that screen, where you have a simulated amplifier in our example today. You can do already some basic spectral measurements directly in the Cadence environment, as you see also here on the right side. But to take it one step further, and nowadays everyone is looking not only on spectral measurements, but also on signal performance like EVM. And to do those EVM measurements, you have to have the right signal going into the scenario, meaning a 5G, a Wi-Fi signal. And you also need to have the ability to do the demodulation capabilities according to the standards. And that is exactly where Rohde Schwarz comes in. In that scenario, what we have here is, you see an input block where you can grab the signal from the signal generation tools, and where you can also forward it towards the signal analysis tools. Andy, you want to have a quick introduction about the VSS solution we are using today?
Yes, of course. Thank you, Markus.
Thank you.
So Cadence acquired AWR in January 2020, and with that came the Visual System Simulator. This is a C++ simulation tool that works with complex modulation schemes. In this case, this is a 5G signal that we read from software. We're prototyping the design tools inside software before spending money, but we can also talk to the hardware equipment that you'll see later on during the presentation as well. It allows us to look at, in this case, pre-distortion of amplifiers, how to correct that and get the best performance for the device with inside simulation before spending money. So Visual System Simulator, the software from AWR Cadence, is looking at sample time domain in terms of the system build-up. We've got a very simple down converter example here where we're looking at signals, potentially complex signals coming through filters and amplifiers, giving us the ability to do cascaded analysis through the design, looking at cascaded gain or noise figure, and also the spectrum that's generated from the signals. We can then take that with the complex modulation signal and run that through the system simulation tool in terms of time domain and spectral measurements, looking at the constellation and the spectrum that we have from that. The example that we'll show you shortly will have something a little bit more complex than this QAM signal here. It will be a 5G radio signal. A lot of proprietary IP behind that, and that's where the link with the Rohde Schwarz test equipment becomes very important to have safe and secure.
Okay, thank you, Andy. So what we are taking here, you see already here the results of the DPD. How does it work? Well, what we have done is you create a signal, you send it through that scenario, and then in order to measure it, it's basically sent out from the VSS, grabbed automatically by the Rohde Schwarz VSE software, which is basically the demodulation capability. So this is where you get the EVM figures. Now, in order to get an understanding how good a device really can be, you want to do linearization, as Andy mentioned. And this linearization can run in this joint scenario where we are doing something what we call direct DPD. We have the very same thing also implemented on the instrument. So what we are running here in the software is exactly the same algorithm, the same methodology as we also have in the instrument to guarantee best correlation between the two sides of simulation and hardware testing. So the ability now for this scenario is, which it gives you, is to understand linearity capabilities to get best possible performance already in simulation before you have hardware on the table. Now, running through this scenario, this software here creates the direct DPD waveform and is pumping it again through the simulation, and that's where you see the different steps on here with the improvement of the ACLR in this example. In VSE, you saw the result of the EVM result after the last iteration step, which provides best possible EVM already. Now, when we take that to the next step for the design process, now you have designed the amplifier in the simulation world, you send it over to the fab, you get the device back. Now, this is the point where you want to hand over to hardware measurements. So what we have here is a vector signal generator and a vector signal analyzer, vice versa. And we are running here exactly the same signal inside of the instrument. We are doing the same methodology inside of the analyzer with regards to EVM measurement as well as the direct DPD. So you can directly compare measurements on the simulation and then with the hardware which you get back from your tape out. Andy, you want to add anything on the simulation piece or some background there?
Thank you, Marcus. It's really important to remember these new modulation signals, such as 5G, are really quite complex, and it's hard to generate those without the software giving you an identical signal in simulation and hardware. So it's important that we're using the same test sources. It's also important that they're encrypted between the software and the hardware units themselves. So we can't just suck those out and use them anywhere else. They need to be linked with the Rohde Schwarz test equipment in the first instance. The predicted performance improvements with the DPD is critical to get the best performance out of the amplifier, the corrections of that, and ensure that we're getting the best efficiencies. And from there we can duplicate that in hardware measurement and prove that actually that correction algorithm is doing what it should.